Every time you look out at night, you would have most definitely seen a large, pale sphere sitting in the night sky. The moon. We don't think of it much, but our moon has a far more unexpected role for our planet than what we may think. Hello everyone, and welcome back to the C-Squared channel. Our moon is our only natural satellite, orbiting our planet roughly every 27 days. We've made quite a lot of achievements around it, such as visiting it ourselves, and more recently discovering liquid water on the surface. But did you know that it is responsible for something rather interesting on the surface of the Earth as well? It's true! Our moon has a direct effect on the oceans on the surface of the Earth. It is actually responsible for the tides on our shorelines and in some rare cases unusually large waves across the oceans, which we could see happen from all across the world. But how does the moon achieve this? The reason is all because of two key factors: the moon's orbit and its gravitational influence on the Earth. To begin with, our moon has a near-circular orbit, meaning that it orbits a planet in an almost circular path. So this type of orbit we call an elliptical orbit. You can see this orbit as a bit more of an X shape if you like. And as it moves, there are special points where the moon can be either the closest on one side and farthest on the opposite side. So we have this kind of exaggerated model of a planetary system here. We can consider point S to be the Sun, and point B to be just a planet. So the closest approach to the Sun is the one where the planet will be kind of right next to it, and we call that the perihelion. Likewise, the farthest approach, which is on the left there, where you can see the planet will be furthest away from the Sun, is called the aphelion. Now, if we want to change this into a model of our planetary system with the Earth and the Moon, then we simply consider point S to be the Earth instead, and point B would be the Moon. And what's crazy is that this relation is still somewhat accurate. The only exception is, well, obviously, the Moon does not orbit in such an exaggerated way like this, and it's more almost circular. Why does this affect the oceans on the Earth? Well, this nicely leads on to my next key factor, which is the gravitational influence. Everything around us generates a gravitational field, including any object, animal, plant, human, so on and so forth, on Earth and anywhere else in the universe. The strength of these gravitational fields, from a classical perspective, is dependent on how large and how massive an object is, typically given through this equation, which is the gravitational field strength. So naturally, we wouldn't really feel any of the gravitational fields produced by us or other objects on the Earth, and the simple reason is because the gravity of the Earth itself dominates over everything on the planet. So we only feel the Earth's pull, instead of, say, each other or, some other object that might be next to us. But that's not the only gravitational field that can be experienced on the Earth. Oh no, our moon is also large enough to influence the Earth with its own gravitational field. It's still quite weak though, at a strength that is about, say, 6 times less than the Earth's. We can see for ourselves that it's still enough to affect our planet in some way. So as the moon orbits a planet, the gravitational fields between the moon and the Earth are constantly interacting and interfering with each other. This actually results in the Earth being slightly deformed from its usual sphere structure to something that we call a spheroid. This is because gravity from the moon is very slightly squashing and stretching the Earth so that it actually bulges a little. This effect is what is known as a tidal force, and this is the main reason why we actually have tides across our oceans. Because the Earth is stretching out, water will tend to collect up near the bulges of the Earth, and we can see this as a high tide. So when sea levels on the coasts are quite high. In the areas that are far from the bulges, you would expect to have less water, because some of it moves to the bulges, and so this is a low tide. During the course of the day, and throughout the moon's 27-day orbital period, the high and low tides would be constantly switching places across the world. The moon has the dominant tidal forces on the Earth, but the sun can also have a significant effect as well. Depending on how the moon and sun are aligned, they can either amplify the tides of the ocean or weaken them. To put it very simply, if the moon and sun are lined up nicely, we get an effect that is known as a spring tide, where the tidal forces of the moon and the sun are added together. This results in a much larger tidal force, and so we can expect a very high tide on the Earth. Much higher than what should be expected. Likewise, we can have an opposite effect happen if the moon and the sun are 90 degrees apart from each other. Kind of like as shown in this arrangement here. In this case, the tidal forces actually end up counteracting each other. So in other words, the tidal forces from the sun can be subtracted from those from the moon. And we are left with something that is known as a neap tide, which means that the Earth hasn't been squashed and stretched as much, and the high tides you'd expect will be somewhat diminished. It's not a full cancellation though, since the moon's tidal forces are generally larger than the sun's, but the result will certainly be far less than what should be expected for a high tide. As the orbit of the moon isn't a perfect circle, we can bring back what I said earlier about its elliptical path. If we ignore the additional factor of the sun's tidal forces for just a moment and focus solely on the moon's, we could see that the distance of the moon from the Earth also has an effect on these tidal forces, and it would be most obvious at the extreme points of its orbit as it moves around us. Although because it is near circular, it would not have too much of an effect, but it still has some kind of an effect in general. At the perihelion, you can expect there to be greater tidal forces because the moon is closest to the Earth, and so this would have slightly stronger gravitational influences, and we'll get more than average high tides on the coastline. Similarly, at its aphelion, you can expect the tidal forces will be at its weakest since it is the farthest away, and once again we can see that the gravitational influences will therefore be weaker, and this will give us less than average tides on the coastline. Finally, we can put all of what we talked about today together to explain the main point of interest for this video. How does the moon affect the ocean tides down here on Earth? It's known that the moon's gravitational field is constantly interacting with the Earth's, and this interaction creates what is known as tidal forces that squash and stretch a planet ever so slightly. This gives a rise in ocean tides on the bulges of the stretching, while giving low tides in areas that are quite far from the bulges. Additionally, depending on where the moon is during its orbit, these tidal forces can be strongest at its closest approach to us, and weakest at its farthest approach, with the sun playing a part in either amplifying or diminishing this tidal effect on the coastlines. So with all that said, it is rather mesmerizing how a companion moon like ours can have such an insane effect on the way the oceans move and circulate around the planet. It's so important that without a moon, the tides we see on Earth would have been extremely weak, and the way we see how oceans moved would have been so very different as well. Thank you guys so much for watching this video, and I'll see you all in the next one.